everyone. I Anshul Sharma, Vice Chair IEEE NTC Student Chapter, ACSI or CSIO. Welcome you all for today's session in Electrochemistry webinar series, jointly organized by IEEE NTC Student Chapter, ACSI or CSIO, Electrochemical Society of India, and SRM Institute of Science and Technology, and IEEE Chandigarh subsection. So we are especially honored to welcome Dr. Shantanu Bhattacharya, Director CSIR CSIO, Professor E. Dwarkadas, Professor ISC Bangalore, ex-President ECSI, Professor Aruna, President ECSI, Professor Ramanujam, Professor IIT Madras, and the speaker for today's lecture, Professor Satish, IEEE Student Branch Counselor, CSIR, CSIO, and other respected faculty members and guests who have joined us today. Thank you for your presence and continued support. So to begin the event, I request Dr. Pooja, Advisor IEEE NTC, ACSIR, CSIO, and the Governing Council member ECSI to give the brief about the series. So over to you, Dr. Pooja.
Thank you, Achal. So first of all, at the outset, I would like to thank our director, Professor Shantanu, and branch counselor IEEE ACR CSIO, Professor Satish, and President of Electrochemical Society of India for their encouragement to conduct this series. So this series was conceptualized as a skill platform for the young generation students to know about electrochemical techniques, especially for their understanding of the concept and their use in the emerging technologies. And this is the first lecture in this series, and I'm happy to inform we had more than 450 plus registration for this first talk by Professor Ramanujam. And we are seeing that students are now joining. We have around 174 students who have joined. So I'm also thankful to Professor Ramanujam for accepting our invitation at a very short notice. And so without further ado, I will start by inviting our director, Professor Shantanu, to deliver his opening remarks. Over to you, sir.
Yeah, thank you, Dr. Pooja. Indeed, it's a pleasure and an honor to initiate these seminar series from CSIR, CSIO side. In fact, looking at the energy landscape and looking at today's storage solution,
Sir, we are not able to hear you somehow. Your voice got cut in between.
Am I audible now again?
Yes, sir. Now you're back.
Yeah, sorry. I mean, there is some connectivity issue because I am also sort of, in the middle of travel and all. So I'll again start. So I think where was I when I was lost? I think it's somewhere around CSR, CSIO that I was talking about.
Yeah.
Okay. So this particular series, the electrochemistry webinar series, it's really a very great initiative. I must congratulate both the IEEE NTC chapter as well as our CSR, CSIO student chapter and also the Electrochemical Society of India. Of course, it's a very invaluable window into the latest technological frontiers in electrochemistry. The technological insights shared from the intricate design of fuel cells to the development of high-performance electrochemical sensors, all of it is a sort of testament to the immense innovative potential within this field. From discussions on fundamental understanding with practical technological applications such as interdisciplinary discourse, it is crucial for driving technological breakthroughs. And I'm sure that our younger generation will gather a lot of thoughts for carrying out innovative research in this very important domain for our country. So I'm very strongly of the opinion that the series would actually serve as a powerful catalyst for inspiring both new research directions and also accelerate technological progress. Today's speaker, I think, doesn't need any introduction by itself. I mean, if you look at his domain of work and, also what he's going to talk about today, Professor Ramanujan is quite well known in the area of redox flow batteries. And I'm sure the interaction that he would make with all of you more towards the fundamental. I was very happy to see that he pulled on a screen and started to tell all of you whether he can write on the screen and tell you about the research and all. So I think that's a wonderful aspect of an educator, an academician, that whenever you interact with students, you actually go to the fundamentals and talk about from the basic fundamental equation state how you can interpret science and then later on technology. So again, a warm welcome to all of you, and I wish this seminar series a grand success. Thank you very much. Over to Pooja.
Thank you, Professor Bhattacharya, for your insightful opening remarks. We truly appreciate your thoughtful words and the context you have provided to start this event. Now I request Professor Aruna, President ECSI, for her brief remarks. Professor Aruna?
Yeah. Good afternoon to everyone, and I'm really happy that we are seeing a good, amalgamation of the student chapters, ECSI, and also SRM University. It's really a good amalgamation of all the, kind of research and students and so on. So, and I'm very happy that Dr. Pooja has taken this initiative. And I'm very happy to see that so many students have joined online, and I'm sure that all the students will be benefited from this webinar series. And she has taken care of choosing very good faculty, and I'm happy that today Professor Kodanraman is delivering the first lecture, and we look forward to great learning and good interactions. And I request all of you to take active part in this webinar series and also become active members of our Electrochemical Society of India. And we all know that electrochemistry is a perennial subject, and it keeps on growing. It's like the Hanuman tail, okay, it will keep on spreading its tail everywhere. So it's very, very crucial subject, and it's very important that we learn all the fundamentals. And I wish all the success for this webinar series. And I once again thank all the people who have taken immense efforts in organizing this webinar series. I also thank Director CSIO for his opening remarks and taking part in this opening webinar series. Thank you.
Thank you, Professor Aruna, for your kind and inspiring opening remarks. It is now my pleasure to introduce today's distinguished speaker, Professor Ramanujam, who is a faculty member in the Department of Chemistry at IIT Madras, where he has been serving since 2011. He is also an adjunct faculty at the National Center of Catalysis Research at IIT Madras. He is a pioneer in electrochemical research and has developed key battery technologies. He completed his PhD from IIT Bangalore in material electrochemistry and went on to pursue postdoctoral research at Michigan State University and the National Research Council of Canada. His work focuses on electrochemical energy storage, redox active materials, and sensors. He is the recipient of several prestigious awards, including CRSI Bronze Medal 2023 and Amaraja Award 2021, and he is also Fellow of Royal Society of Chemistry and the Academy of Sciences, Chennai. So without any further delay, I request Professor Ramanujam for his lecture on fundamental of impedance characterization techniques. which is a core electrocatalytic method in electrochemistry for energy and sensor technologies. We are truly privileged to have him with us today. Before we begin this lecture, I kindly request all the participants to keep their microphones muted for any disturbance. Please feel free to type your questions in the chat box during the lecture. And also you can raise your hands during the Q&A sessions, which we'll be having after the lectures. So over to you, Professor Ramanujam.
Okay, thank you very much. Can you hear me now?
Yes, sir.
Yeah, okay. So thank you very much. So I thank Professor Shantanu, Dr. Pooja, Dr. Aruna, Mayalagan, and other members who organized this, and also the participants for joining this online seminar series. Actually, I planned through iPad so that I can write with my pencil. But anyway, I will try doing it through my computer as well. Let's see how it goes. Since the students of varying background would be there, so I made it as simple as possible without involving too much of mathematics, so that you can appreciate the tool impedance spectroscopy. How can this be used for the battery characterizations particularly? So why are we using this impedance spectroscopy? Impedance spectroscopy alone may not be useful in the characterization of the batteries. Probably you may have to combine it with other technologies, spectroscopies, or other technology like cyclic voltammetry, charge-to-charge cycling, or any other analytical technique that is available. So if you want to make a sense out of it. But once we know battery is made and we know how, what kind of path it takes during its lifetime, so we can use impedance as a non-destructive tool, so without needing to open the battery every time, and then understanding what changes as the battery ages, or during charge discharge with the time. So that kind of analysis can be done with impedance spectroscopy. It's particularly very interesting. You can see in the next slide, there are various processes that happens in a battery when you run, or in any electrochemical systems when you run it. For example, if you consider a lithium-ion battery, say we look at the charging of the lithium-ion battery. Okay, so if you are charging, so from the cathode you are extracting lithium ion, and that gets intercalated in the anode, which is graphite in nature. So let me take out this slide and go for the whiteboard so that I can better explain that. Let me see. I can do that. That's switching. Okay, for switching, I have to stop, then do. Okay, so can you see now my whiteboard?
Yes, sir.
Okay, fine. So now you see, you have, say, for example, lithium cobalt oxide. So when you are charging, what you would do, you would be extracting lithium from this. So you'll get some X amount of lithium coming out as lithium ion. So proportional amount of electron has to come out from the cathode. And what you left with is Li 1 minus X, then CO X, then another CO, which is 1 minus X O2. Okay. Sorry, this writing is not that good because I'm not using pencil. So if you look at it, this X electron is coming out of this redox element which is here, which is cobalt, transition metal. So this particular cobalt initially in 3+ oxidation state, once it loses X electron, so X cobalt will go to 4+ oxidation state. Okay, the remaining cobalt will be in 3+ oxidation state. Okay, so now this lithium has to intercalate into the graphite, which is your anode material. The graphite, has a layers of graphene, which you can see, and these graphene, in between these graphene, okay, this is very erratic, not working well. Okay, now. So now this lithium will get intercalate into these graphitic layers. Okay, in between those layers, along with this, the electron will go to the graphene layer, so it will become negatively charged. The lithium will be in between the graphene layers. So electrostatically, this is how it will be held. But this looks so simple, but there are a lot of processes involved. For example, lithium cobalt oxide is a solid. Okay, so lithium has to diffuse into that solid and then come out of the boundary and then enter into the electrolyte. The moment lithium enters the electrolyte, the lithium ion will be solvated by the solvent molecules which is in the electrolyte. So it will become really bulky. Then it has to transport itself towards the anode, which is a graphite here. Okay. So lithium has to diffuse in the solid state material, lithium cobalt oxide, and then it will get solvate. Then it will travel towards your anode material. So that traveling can be any transport process like diffusion or convection or by migration. Then again, when it comes to anode, it has to intercalate itself into the anode. So it has to move in the anode matrix. Before moving, in the anode, generally we have something called SEI, solid electrolyte interface. Okay, this is an interface that is formed with the initial amount of lithium that went inside the graphite electrode, and that is reacting with the electrolyte. So it forms some products. Okay, those products is solid in nature, and they get deposited on this electrode itself. But it is called solid electrolyte interface because it allows the lithium ion alone to go through it, but not the electron. So it's ionically conducting, but not electronically. Okay, so therefore there is a resistance for the lithium ion to move through this SEI layer. Okay, and there is a a diffusion coefficient associated with the lithium which is moving in the electrolyte. Okay, and then it gets intercalated here. So if you see, it is a lot of processes here. One is there is a redox process at the anode, there is a redox process at the cathode, and there is a transport of the species in the solution, and then the species has to diffuse through the SEI layer that is present. Okay, so there are many events which happens simultaneously during the charging discharging of this battery. Okay, now each of those event can be understood using impedance spectroscopy. They are using something called a time constant. Okay, because each of those event takes a different possesses different time constant. Therefore, we can distinguish them in a impedance spectroscopy. So now if you can see in this table, I have listed several processes here. For example, electronic conduction that is happening within the electrode or the solid electrodes and the current collectors and so on. So these will respond in a time scale less than 1 microsecond. That means their frequency range will be above 1 megahertz. Typically, we don't have the instrument in our laboratory. The common potentiostat, galvanostat that we use does not go beyond 1 megahertz. Okay, so we cannot see this so well. So this is typically very fast. So the impedance will not, the minimal impedance changes unless this is an inductive in nature. Otherwise, if it's a simple conductor, you wouldn't say any change in impedance of this particular process with the change in frequency. So. And you look at the double layer chargings, because you have an electrode dipped in the electrolyte. So as soon as an electrode dipped in the electrolyte, a double layer that forms, and charging, discharging of that layer responds in this type of time scale. So therefore, in your impedance spectroscopy, the inverse of these 10 power minus 3 is 1 kilo, 10 power minus 6, 1 megahertz. So in this range, you will see a capacity behavior of the electrode electrolyte interface. Okay. Now, if you look at the charge transfer reactions, which are happening between millisecond 10 power minus 3 millisecond time scale to a seconds time scale. So now if you see, they work in the this is a Faraday process. Okay, so they respond in the frequency range 0.1 hertz to 10 kilohertz. Okay, and now if you look at the diffusion. Okay, so many of you know the word Warburg impedance. Okay, so the diffusion responses happens in 1 to 100 seconds or longer. So that is 0.01 to 0.1 hertz is a region where you would see they would respond. Suppose you have absorption and desorption in the process, then it would be between 0.1 to 100 hertz region in which you would see. Okay, and if you look at the bulk electrolyte conduction, so that means the conductivity, if it is very high, then you would see them responding at high frequency. Okay, and these are the but in general, if you categorize at high frequency region, you will be able to probe the electronic processes and the double layer capacitance. In the mid frequency regions, you will be able to look at the charge transfer resistance and in the low frequency region, you will be able to look at the mass transport processes. Okay. So now let's stick to the battery if you want to look at it. So you can see the electronic conduction in the range, as I said, above 1 megahertz, and the electrolyte resistance, that is a separator that you have. So they will respond in microsecond to millisecond region. That means in kilohertz to megahertz region, and double layer, as I said, in kilohertz to 100 kilohertz region. And the charge transfer reaction, like a cobalt, which was switching its oxidation state in case of lithium-ion battery, which I discussed, which will happen in hertz to kilohertz region. And if you have a solid electrolyte interface, so resistance due to the solid electrolyte interface, you would see anywhere between 0.1 hertz to 100 hertz. Okay. So on the lithium-ion diffusion into the electrode, because that is the slowest process that you would see, in the entire battery. You can have a redox reaction also maybe faster, but that lithium which is intercalated into the electrode has to move, so that the next lithium comes and intercalates through that window. So you will see that is very slowest process. That happens in 1 millihertz to 0.1 hertz type of frequency range. So this is a typical time constants that you should remember when you are characterizing battery, because if you see any impedance features in these frequency range, you can quickly think of, suppose you have impedance features in this range, then you can quickly think of it is something related to the lithium-ion diffusion in the electrodes and so on. Okay. So now let's go to the fundamentals. So how do we actually do this impedance characterization? It's very simple. You can have a single sine wave or a multi-sine wave as your input, but now I am going to explain you using a single sine wave. So let's say I am going to apply a potential to the electrode-electrolyte interface. Okay. So I'm going to apply potential to an electrode-electrolyte interface such that you can see here, such that a 50 millivolt, okay, from the open circuit potential, I goes 50 millivolt above or 50 millivolt below. That means my perturbation in the form of voltage, which I'm going to apply, is about plus or minus 50 millivolt. Okay. So your DC potential can be anything. It can be 0 or it can be open circuit potential. It can be some value, say 0.4, 0.5, 0.6 volt, whatever you want. So you can characterize the battery at the specific state of charge. That means at any specific voltage, or you can characterize the battery at open circuit condition after completely discharging as well. Okay. So now when you apply this frequency input on the this terminal of battery terminal, then you would see when if it is a simple, imagine first I start with a simple resistor, for example. Okay. So now if I apply a sine wave, then I would get a, just a second. Okay. If I apply a sine wave, so the sine wave I'm applying here, I have given that equation. So E is the voltage, so voltage at a given time. Okay. E AC naught is the amplitude, which is here in this case about 50 millivolt. Okay. And this is angular frequency omega, T is the time. Okay. So as the time progress, you will see this amplitude is manipulated by this sine wave and you get a voltage, right? So that's the voltage that is along this line. Okay. Okay. So you can convert angular frequency to a linear frequency using this equation, which I have given here. Okay. So when you apply a voltage perturbation to a system, then it will in response, it will give a current as a response to this perturbation. So from this applied voltage and also in response to what is the current you got, so combining these two, we will be able to identify what is the impedance of this system. Okay. Now you see here, I am going to choose a resistor which is 2 ohm in magnitude. Okay. So instead of going for a battery first, let us start with a resistor. Okay. So if we take this resistor, so which has a magnitude of about 2 ohm, and I'm going to apply a voltage, perturbation of about 50 millivolt, sinusoidal form. Okay. So then you have a 2 ohm and this is 50 millivolt. So 50 divided by 2, that is 25. So you will have a current response, which is about 25 milliampere. Correct. So that's what I have plotted in the here in the blue lines. Okay. But what is interesting here, if it is a pure resistor, when the voltage applied across the resistor is 0, your current is also 0. Okay. As the voltage rises, the current also rises. So what is the magnitude of the maximum current? That depends on what is the magnitude of the resistance. So if the resistance is lower, your current can be higher. If the resistance is bigger, your current will be lower. Okay. So if you see the profile of your potential as well as the voltage, they are in sync in terms of phase. So there is no phase difference between them. So that is the characteristic of the resistor. So this property of resistor is called resistance. Now let us do that using a different frequency. In this case, I have chosen not a different frequency. I have chosen a different resistance. Instead of 2 ohm, I have taken here 0.5 ohm. So we take 0.5 ohm. E is 50. 50 divided by 0.5 is 100. You see now the current has gone to 100. Okay, not necessary that the current output has to be lower than your voltage. Not necessary, right? It depends on the magnitude of the resistance that you have. But again here, even though I changed the resistance, still the voltage and current profiles are in sync. Okay. Now what I have done in this particular case, I have done it at 1 Hertz frequency. What is 1 Hertz? 1 Hertz means one wave that passes in every second. Okay. Now you can see here, starting from here, going like this up to here is one wave. So that one wave is fitted in 1 second duration, right? So therefore, this is 1 cycle per second, which is 1 Hertz. Okay. Whereas in this case, this is 1 second is here, but you can see there are 3 waves which are already fitted here. Okay. That means this is 3 cycles per second, which is 3 Hertz. Correct. So I have increased the number of times I go up and down. Okay. Number of times I excurse to plus 50 millivolt and minus 50 millivolt. I have changed it. It is 3 times in 1 second. Right. So therefore, this is 3 Hertz. Whether it is 1 Hertz or 3 Hertz or 10 Hertz or 1000 Hertz, I still see the current and voltage are in phase. There is no change. Okay. So they are absolutely equal. Why? Because we know when I apply a voltage waveform E, then it is a proportional current waveform you get. Only thing you will see, the magnitude of the current will change depending upon the value of the resistance. So that's a simple relation between the I and E here. This is Ohm's law. So therefore, there is no phase difference. Now let us do the same thing using a capacitor. Okay. So in capacitor, let us see, I have a current response or voltage perturbation, which is E AC naught sine omega t. So what would be the current if I apply this voltage perturbation? And we know the current is related to voltage through this capacitance. C is a capacitance here. So I is equal to C into dE by dt. So you might have heard this famous relation C, capacitance is Q by V. Q is the charge that is stored in the capacitor under the potential difference of V, right? So now you differentiate that, you see it's a dQ by dt. You can also denominator, you do the same thing, dV by dt. You will see dQ by dt is nothing but current. dV by dt is nothing but the scan rate. So that's the equation I have given over here. Okay. So now you can see I have to differentiate with respect to time once this perturbation. If I do that, what you get, the omega comes out, it becomes C omega EAC naught. Sine when you differentiate becomes cosine omega t. And we know this trigonometry relation, cos omega t is nothing but sine omega t plus pi by 2. So I substitute here. So now if you compare this with the Ohm's equation, okay, so what is Ohm's equation? IR is equal to V, right? IR. So what is R here? This is a V here. Sine omega t. So R will be then 1 over C omega, right? Because you move this to the left hand side, it becomes I by C omega. So that if you then you can equate this equation to the Ohm's law, IR is equal to V. Then you would see in place of R, what you have is 1 by C omega, right? So that C omega is kind of decides the resistance here. Okay, but omega is a frequency which is a variable. Therefore, the resistance offered by a capacitor depends on the frequency at which you are probing. Okay, so it is not fixed. In case of resistor, whatever may be the frequency, resistance was same. Whereas in case of capacitor, okay, the resistance offered by the capacitor is now a function of the omega, which is angular frequency. Therefore, we don't use the same term resistance here to define what is a here. We will call it as a impedance. Okay, so impedance is a common term which includes any passive elements, whether it's a resistor, capacitor, inductor, whatever it is. So it is common to all of them. Okay, because it includes also phase information, right? So now let us look at this at 3 hertz frequency using a capacitance of 20 millifarad. So when I do it at 1 hertz, this is a voltage waveform, and you see there is a response. In response to that, there is a current waveform. But what is interesting, when the voltage is 0, the current was maximum. When voltage is maximum, the current is 0. Clear? You see, there is a 90-degree shift between the maximum of current and the voltage. Okay, so that's because this is a capacitor. It has a very complicated impedance profile. Okay, and then if you look at the 3 hertz case, okay, everything else same. My voltage perturbation is same. My capacitance of the capacitor is same. Only thing I changed is the frequency. When I change the frequency, one more additional change you see, which is the magnitude of the current. Here the magnitude of current is very small. Here with increasing frequency, I see the magnitude of the current going up. Okay, whereas in case of pure resistor, the magnitude of the current was not changing irrespective of the frequency, whereas here this is started changing. Okay, so now if I go to very high frequency, infinite frequency, you would see the current also will go to infinity. Okay, you can think in a different way here. For example, if we have a let's assume we have a 2 glass. Okay, one glass is filled with water. I am going to transfer that water from between the glasses. Okay, I want to do first one time in 1 second. Then I wanted to do it 3 times in 1 second. Then what will happen? You have to transfer the water from one glass to other glass, but earlier you were doing it in 1 second, but now you are asked to do that 3 times in 1 second. That means you have to quickly transfer. That means the flow rate of water from one glass to the another glass, the tumbler, it's increasing now. Only if you do it very fast transfer, you can do 3 times in 1 second. Similarly, if I ask you to do it 10 times, then 10 times you have to change the water from one glass to the another glass. Then the flow rate has to be further increased. So the current is like the flow rate only here. What is flowing here in the current? In the current, it is the charge that is flowing. In case of water transfer, it is the water that was flowing. In here, it is a charge that is flowing from one electrode to the other electrode. So since I am doing that high frequency, the charge has to move from one electrode to the other electrode very quickly. That is what we have to look at it. Now, we can do the same thing for an inductor. So inductor also, you see a phase change, phase shift when you go from between the voltage and current waveform. But here you can see the voltage current trails the voltage, whereas in this case the current was leading the voltage. That meaning when the voltage is 0, current is maximum. So current was leading the voltage by a phase pi by 2. Okay, whereas in inductor it is opposite, it's a negative pi by 2. Okay, so and here also I have shown you at a different frequency how you see this induction happens. Once again, when you increase the frequency, you see the magnitude of the current falls in this case. Okay, whereas it was growing in the case of capacitor. I hope all of you with me because I'm not seeing the participants in my screen. Yeah. Yes, Dr. Pooja, right?
Yes.
Yes. Okay. Sorry about it. So now let us do impedance. Before doing that, let's look at one electrode-electrolyte interface. Okay. So an electrode-electrolyte interface can be considered a combination of certain passive elements, because when you apply over potential, for example, to an electrode, what happens with increasing over potential? The current density increase, correct? So how the current density increase? Because we have seen in the traditional catalysis, when I change the catalyst, an inferior catalyst with a better catalyst, I would see the reaction happening faster. Okay. what basically happening, rate of the reaction is increasing when I change with a better catalyst. Similarly, in electrochemistry, even though with the same electrode we are using, but if I apply a higher over potential, we are able to see an increased current. That equation all of you know probably, we call it a Buttle-Volmer equation. In the Buttle-Volmer equation, the current is related to over potential by an exponential term. Okay, so you can imagine with increasing over potential as if this activation energy related to a charge transfer process is decreasing. Therefore, with over potential, current is increasing. So that's how you can draw an analogy between the regular chemical kinetics, where rate of the reaction is equal to K, which is a rate constant, times concentration if it is a first order reaction. So the K can be further expanded as omega, which is a frequency factor, times e power minus EA by RT, where EA is the activation energy, correct? So now the similar thing we can do in electrochemistry. So you can increase or decrease the activation energy by applying a potential to the electrode-electrolyte interface. Therefore, current admitted through that interface can increase or decrease with the applied potential. Okay, so therefore we can think of that interface as if it is having some variable resistance. Okay, so the R1 which I have given here is fixed for one over potential, but if you are keep on changing the over potential, this R can change, because this R is something higher the R, greater the impedance for the flow of electron. That means less current will flow through this, which can be equated to a chemical process which has got a very high activation energy. If R is smaller, more current can go through it under a given potential drop. Okay, this can be viewed as if you are doing a reaction where activation energy is very small. So therefore, this R is a variable with over potential, and this R can be parallel or considered as analogy to the activation energy in your chemical process. And now we have a capacitor here, because every electrode-electrolyte interface has a double layer. Okay, so you might have studied about the Helmholtz double layer and Stern double layer and so on, right? So that's not the purview. The detailed discussion on that is not part of this lecture, but you might have heard about it. So every electrode-electrolyte interface has a double layer, so that has a capacity to store charge. Okay, so depending upon what is its capacity, it has got a capacitance that is denoted here. So every electrode-electrolyte interface, independent of whether it is doing a Faraday reaction or not. What is Faraday reaction? Faraday reaction is nothing but the charge transfer reaction. For example, in the lithium battery case that we discussed, what is the Faraday reaction there? Where cobalt was switching between 3+ to 4+. That was a Faraday reaction. Okay, so therefore this can be considered as a capacitance associated with that electrode-electrolyte interface, and the charge transfer reaction is giving you this resistance value here. And all these ions which are intercalating, deintercalating are coming through an electrolyte. So that electrolyte should have some conductivity, otherwise ions will take indefinite time to reach the electrode. Therefore, the conductivity of the electrode defines what is the resistance of that electrolyte. Okay, if the conductivity of the electrolyte is very high, then this resistance which is belong to the electrolyte will be very, very low. But if you notice carefully, these two elements C and R1, I have kept it in parallel. That means they can happen independently at the electrode-electrolyte interface. That means as you are charging the electrode-electrolyte interface, you will be seeing also a charge transfer reaction that is happening. Therefore, these two can be parallel. Whereas whether you are charging the interface or you are doing a charge transfer reaction at the interface, the ion has to come from the solution. Okay, so yeah, mass transfer has to happen from the solution. Therefore, solution resistance, I have kept it in series with this RC parallel element. Okay, this particular simple circuit is called Randall's circuit. Okay, this is called what? Randall's circuit. So with this is normally used to understand the impedance in electrochemistry. Now let me do part by part here. Let's take only this RC parallel part, which is related to electrolyte interface, and this is related to electrolyte. So we are not considering that right now. Now let's look at it. I am going to, in a parallel circuit, we know in a serial circuit, the resistance will add. Suppose I have a resistor followed by another resistor. What is the total resistance? You have to add them simply. Suppose I have two resistors in parallel, then how will you find what is the total resistance? So the effective resistance for which you have to add the admittance together. Okay, so that's what I'm doing here. Here I have drawn the admittance. Okay, what is the admittance for this capacitor thing? You remember I derived that equation where I was equal to, you know, omega c e naught cos omega t plus, right? So that omega c we have taken to the left hand side, and I call that as a resistance. Now we are looking at the admittance. Okay, so 1 over 1 by omega c, that becomes omega c, right? So that is going to be the admittance of this part, and I put a j here. The j has a value of root of -1. So why did I have this here? Because remember, the impedance in case of resistor is a resistance, whereas in case of capacitor we call impedance because it has a phase information. So to introduce the phase information, so I have brought in this j over here. So the admittance now will add. What is the admittance of this resistor? This is 1 over R. So you add the admittance of this, and you get the total admittance. And you take the inverse of that, then you get the impedance of this part in the box. Okay, impedance of this part in the box. Now go to the next step. Now I wanted to simplify. So cross multiply this and you get this. Then I multiply by this 1 minus R j omega c. Then you would get something like this. The interesting part here is you have something which is fully real. Okay, this is a real part, and there is something which is fully imaginary because this is j times this. So I express this in the form of a complex number now, like x plus iy, something like that, right? It's like or a plus ib type of a complex number I have represented here. Now I am going to find the total impedance of this random circuit, which is very simple. The total impedance is nothing but take this, add to this impedance which we calculated over here. So then this R naught along with this part will become the real impedance, because the real part of the complex number, and this is the imaginary part, that is R1 squared omega c 1 plus R1 squared omega squared c squared. Now we can play considering some extreme conditions. For example, I have a situation where I am applying this voltage perturbation at a very high frequency. When you apply at very high frequency, how the current will flow? The current will flow through this, and then it has a choice. It can go like this or it can go like this, or it can divide itself in both the arms. But what will happen with very high frequency? Remember, in case of capacitors, if you go back and see if you want, in case of capacitor, I have shown when you increase the frequency, the current magnitude increases. That means with increasing frequency, the impedance kind of decreasing for a capacitor, right? So therefore, with increase, if we go to infinite frequency, what will happen? The impedance will be nearly zero in case of capacitor. Therefore, all the current will go through this. And what you would see under that condition is only the resistance of the electrolyte. You won't see anything else if you do the experiment under that condition. So we can also verify this using this equation. If my frequency omega is infinity, then this term will become 0. This term also, okay, because this is omega square. So this is going to be also 0. So what your total impedance depends on now, it's only R naught, which is a solution resistance. Whereas if you do the other way, if I am doing that very low frequency, at very low frequency, the impedance of the capacitor will be very high. Therefore, current will not go through at all. So the current will go through R naught and R1. Okay, so impedance at very low frequency will be sum of R naught and R1. Let us check that. At very low frequency, what will happen? This term here is negligible compared to 1. Then it will become R naught plus R1. And at very low frequency, what happens? At very low frequency, again, this term will disappear. Therefore, you will have only total impedance as R naught plus R1 here, correct? Now, let us look at one example with some numbers given to those passive elements. Let's say R naught. R naught has got 10 ohm here, and R1 has 100 ohm, and C, which is a capacitance, is 10 power minus 5 farad. Okay. So now let's do this calculation. You can use this equation. All you need to do is I have given the value for the R0, I have given value for R1, I have given value for C. And now all you need to do, you have to assume different frequency, okay, omega, say from 1 megahertz to 0.1 millihertz or something, different frequency you can assume. And at each decade, for example, from 1 megahertz to 10 power 6 hertz to 10 power 5 hertz, that's 1 decade, or 10 power 5 hertz to 10 power 4 hertz is 1 decade. So in each decade, you can choose some 6 frequency, 7 frequency, whatever you want. And then if you can construct a spectrum wherein you assume a frequency ranging from 1 megahertz to some millihertz, and you are going to input those values in this equation, and I have given you the value of R0, R1, and C, and then you can calculate the ZT. Also, you can calculate what is the real part of the impedance, what is the imaginary part of the impedance also. So all that you can calculate, and then you can draw this plot. What is the total impedance? Total impedance is, because that's the way I have represented was a a complex number. So from there you can understand the total impedance is square root of Z real plus Z imaginary. And what is the phase? So phase is the tan inverse of Z imaginary by Z real, right? So because this comes from your Pythagoras theorem, you can use and understand. When Z defines the square root of this, then you will know what is the phase. It can be defined like this. So now if you look at it, if I plot, if I find out what is the Z real and what is the Z imaginary, how do I know at a different frequency? See, this is at a point, each point here is one frequency, right? I told you to do that by simply using this equation, right? You take an Excel and you can compute those. It's very simple. And then you can now plot the Z real, Z imaginary versus Z real, and this left hand side is generally given to the high frequency and the right hand side is given to the low frequency. And this plot is called a Nyquist plot, okay, Nyquist plot. So at high frequency, what will happen? Remember, at high frequency, capacitor won't come into picture because there is no impedance due to capacitor, okay, because capacitor act like a short at that condition. So your main impedance comes from the solution. So what you have at high frequency here, that value, resistance value, must be due to the solution resistance or solution cum contact resistance, okay, because the contact resistance and solution resistance are the one which responds at a very high frequency. Let's go back and see that table, okay. We look at this table, okay, you see at a very high frequency, what is coming? At a very high frequency, at greater than 1 megahertz, you have a bulk electrolyte conduction. That means resistance due to the electrolyte, and resistance due to the electronic conduction, which is due to wiring, electrode, that current collector and so on. So at very high frequency, you only see them because your capacitor will act like a short. Okay, clear? Now let's go back here. And as you decrease the frequency, you start seeing some impedance coming, because now the capacitor in the circuit is also taking part in this process. So you will slowly see that coming up, and it will form a semicircle like this for this type of an equation, for this kind of a Randall circuit. And you see at very low frequency, what you see? Remember, at very low frequency, we are current moving through this arm and then through this arm. It was not going through capacitor at all, because capacitor was exhibiting very high impedance at low frequency. So at very low frequency, you would see only the solution resistance, and you would see the charge transfer resistance, and also there is something called Warburg resistance. The Warburg is associated with the diffusion or the mass transport of the electroactive species from the solution to the electrode. Okay, so that can be seen. Okay, so therefore the value that you see here for this particular circuit is sum of R0 plus R1. What is R0? 10. R1 is 100. The addition is 110. So you see 110. So therefore the diameter of the semicircle related to R1, the initial point of the semicircle related to R0. So the final point is sum of this R0 and R1. And this particular frequency over here in the top of the semicircle is called characteristic frequency. So from there we can calculate the time constant. So wherein we can, this one is omega RC equal to 1. Okay. Omega is a frequency, R into C is a time constant. So frequency has 1 hour time. So omega into RC will be a dimensionless number. So omega RC is equal to 1 at this characteristic frequency. Therefore, if I know what is R and here I know what is the frequency, then using omega RC equal to 1 equation, you can calculate what is the C, that is capacitance of this circuit. Okay. So you can take if you have a potentiostat, you can build your own circuit and then analyze its impedance spectra, and you can understand using all that I have taught to you now, the values of these passive elements. Okay. Now we can also plot them in one another way, because in this plot we cannot see the frequency information. If you look at the publication, people generally mention select frequencies, frequency here, frequency here, frequency here. Okay. So we can also plot frequency versus the total impedance. You can see the total impedance at high frequency, it's only depend on R0. So at high frequency, you are having a value of about 10 ohm. But when you go to very low frequency, it is 110 ohm. So at some frequency, characteristic frequency, omega RC, you will see there is a sudden inflection and then it goes like that. Okay. And if you look at the phase angle, again phase angle, remember the phase angle in case of impedance, in case of resistor, when we apply the voltage perturbation, the current was in sync with the voltage. There was no phase difference. Whereas in case of capacitor, there was a phase difference of 90. So at a very high frequency, what you see is only resistor, because capacitor act like a short. At again very low frequency, you see only these two resistors playing. Okay, because capacitor is exhibiting a very high impedance in this case. So therefore, current was going through this arm. Therefore, at very low and very high frequency, you have a phase angle change of 0, but at mid frequencies, you see it goes up to close to 90. Okay, this is a Bode plot that tells you how many RC process or time constant that are present in your system. Each time constant is equivalent to the charge transfer reaction that we have in this case. Okay, this can also be plotted like this using imaginary resistance, how it changes. Okay, again imaginary resistance comes only when you have a capacitance. At low and high frequency, you don't have capacitance because it has role is either it doesn't exhibit any impedance or it exhibits a very high impedance. Therefore, the capacitor role is minimal in these two regions. So only in the mid frequency region you see the capacitance, right? So now we can also have a corrected impedance because we have in this case a R figuring here. So therefore, if you can correct for that R0, so if you correct it from the real value, it's called a total impedance corrected for this solution resistance. You can have them to estimate the exactly what is that characteristic frequency in the system. So now we can do another case wherein imagine I have two reactions which are happening in sequence. So just for an hypothetical case, I'm reducing oxygen. So oxygen initially reducing to peroxide, and then again peroxide is reducing to water. So it's a 2 + 2 electron process. And I assume that it is now sequential. If it is sequential, we can show that charge transfer resistance pertain to the oxygen to peroxide by this branch, and then peroxide to water by this branch, and you have a solution resistance. So you'll have something like this. So in this case, how many semicircles you would get? Generally, people think when you have 2 RCs, then I should get 2 semicircles. It is not necessary, because this is all dependent on what is the time constant. What is time constant? You have to multiply R and C, that gives you in the units of time, right? So that's the time constant. So the time constant tells you, because that has a frequency information, that tells you whether you will get 1 or 2 or merged semicircles. Okay. So in this case, I assumed a certain value here. You can see if I multiply R1 and C1, I get a time constant of 10⁻³ If I multiply R2 and C2, I get a time constant of 6. Okay. So they are about 3 orders of magnitude in difference. Okay. So you would see there are 2 distinct semicircles, because this is belong to one time constant. This is totally belong to a different kind of time constant. Therefore, you see 2 semicircles. Okay. The one which has got the very high time constant. Okay. So where would it come? Because R into C, the one which has got the higher R value and the C value will give the higher time constant, right? So Depending upon what is the time constant, so you would see them coming over here. So now the R1 is 100, okay, this R2 is 200. You can see R1 and C1 has got the very low time constant, so that will come first, and the one which has higher time constant will come next. Okay, so you just because you have drawn like this, not necessary you would expect R1 first, R2 second. No, it all depends on the time constant. The guy who has a lower time constants will appear first because he will appear at high frequency region. Okay. Similarly, you can look at the Border plot. You have a two inflections, and therefore there are two characteristic frequency coming out of these particular examples. Okay. So now, if you continue, let me show one more wherein the time constants are only one order different. Then what will happen? Then you will see they are very close to each other. Therefore, two semicircle appears like a merged semicircle. Okay, they are not very separated because the time constant difference is very small. Therefore, they appear merged. Imagine if these two time constants happens to be the same, then even though there are, as per the mechanism, there are two steps, but it will impedance, it will appear like a one step. So we should not get misled by this. That's why I said only impedance information you cannot believe. You should have some other analytical information which combined with that you can make sense out of it. Okay. So now although I have two RCs, but I have two semicircle, but they are merged. Okay. Now let us look at another example here. Okay, wherein I have taken certain set of parameters over here. Okay, so this is a circuit over here, and then what I'm going to do, I'm taking one more circuit. Okay, for that I have taken certain parameters over here and one more circuit. If you look at it, these three circuits are very different, but their impedance, if you look at it mathematically, they are same. Okay, the impedance equation, if you look at for these three, okay, mathematically they are same. Okay, so therefore by choosing carefully values for this R1, R2, R3, I can see at certain condition all the three equivalent circuits can fit my experimental data. That means for my experimental data there are three solutions now. Then which one I would choose, which is actually happening at my electrode electrolyte interface? I don't know, right? So which one is happening? We don't know. So for that only I said you have to have a help of another analytical technique to confirm which one is actually belong to that given electrode electrolyte interface. Okay, because there is a chance you can have the same output but three different circuit in this case. Okay, so now similarly let us look at this impedance of this. So the Wajid circuit is R1 plus 1 by Y1 plus 1 by Y2. Why? Because these two, you have to calculate the admittance of this, that is Y1. This is admittance of this, that is Y2. So inverse of that will be 1 by Y1. This will be 1 by Y2. That will be the impedance coming from each of those branches. Then add to this impedance, then you get total impedance as R1 plus 1 by Y1 plus 1 by Y2. Similarly, for this one, it will be Maxwell circuit. You will see R4 plus 1 by Y5. What is Y5? Y5 is you have to consider these two. That is 1 by R5 plus 1 by Z6. The Z6 is coming from here, right? So, and then you have to rearrange it and you get here. So, these are the three total impedance equations for these three circuits. Okay. But assuming a proper value for this R1, R2, R3, I can have the same mathematical output. So one has to be careful while fitting and climbing what is happening at the electrode electrolyte interface. Okay. Suppose I assume one value for all of them. I'm not changing. Okay. So I'm not manipulating value. If I assume one value for all of them, you will see that one has a very big semicircle, whereas the Maxwell equation has got a very two small semicircles and so on. Okay. So now, keeping this in mind, how much time I have, Dr. Pooja?
Sir, you can how much it is remaining?
Almost another 10-15 minutes.
Okay, we can have that much time.
Okay, fine, thank you. Because now I am going to show one more example. Okay. So because the students generally encounter when they work on batteries or fuel cells, there is something called Warburg impedance. Okay. And there are two types of Warburg impedance. One is finite and the another is semi-infinite Warburg. Okay. What is semi-infinite Warburg? See, remember, when you have an electrode-electrolyte interface, you have first a double layer that is forming, and when you are starting the reaction, that means when you are applying over potential to the electrode-electrolyte interface, there is something called diffusion layer that is created. What is diffusion layer? In the beginning, when you apply voltage, you would see before applying voltage, you would see the reactant concentration within the solution, starting from the electrode deep into the solution, is all equal everywhere. There is no change, whether just on the electrode or right side of the electrode into the solution or deep into the solution. You would see the reactant concentration is same. The moment you apply over potential, you would see that suddenly the current goes up. That means a reactant is consumed, a product is formed, right? So now when this happens, the concentration of the reactant near the electrode suddenly decreases, correct? So that's what will happen when you apply over potential. So therefore, near the electrode, there is a region which is now having a lower reactant concentration. Okay. So on that concentration, when the concentration near the electrode is lower, then it will try to get a reactant from the the next point, and if there is no reactant, then it will go to the next point. Therefore, the lower concentration starting from the electrode towards the bulk. Okay, the bulk will have the maximum concentration that possible. At the electrode, you will have the lower concentration that is possible for that given over potential. Then you will have a gradient from the electrode to the electrolyte. Okay, so that's what I have shown here. You can see when the reaction happens. Okay, this animation unfortunately not running. 1 second. Let me go. Here, this is what I wanted to have. So suppose you have an electrode, then you apply your electrode-electrolyte potential, you will have a concentration gradient of the reactant. And this thickness where you have the concentration gradient in the solution side is called diffusion layer. Okay, imagine if this diffusion layer is very large, then the species which is entering the diffusion layer will take time to reach the electrode. Okay, because why the diffusion layer is very large? If species would have diffused faster, the diffusion layer could have been very thin. Because the species is not able to diffuse faster, or the concentration of the species is very low in the solution, we are having a very large diffusion layer. Okay, therefore the species takes time to reach the electrode. In such cases, the resistance associated with the flow of the species towards the electrode is very high. So that kind of model is called a semi-infinite model. But if somehow you ensure this diffusion layer is shrunk, it is made very thin, then what can happen? You can have the species which is entering the diffusion layer reaching the electrode faster. So in that case, the resistance associated with the diffusion of the species is very small. Okay, such a conditions you will have a very finite resistance for the flow of species through the diffusion layer. Whereas if the diffusion layer is very big, when the diffusion layer will be very big, when the concentration of species is low, or when the species is not able to diffuse faster, then you will have that. Okay. So how do I do it experimentally confirm whether I am hit with a semi-infinite diffusion problem or can it be turned into a finite diffusion problem? It is possible. You all may be knowing something called rotating disk electrode, which is used normally in the fuel cell lab to study the ORR, OER reactions. People use it. Okay. So using a diffusion rotating disk electrode, I can rotate the electrode. By rotating the electrode, I will be drawing the solution close to the electrode because of this momentum of the species. So the diffusion layer will not grow, it will be compressed by this flow of liquid. Therefore, at different rotation, for example, at 300 RPM, so what was this is the thickness of my diffusion layer. If I go to 600 RPM, it will decrease further. If I go to 900 RPM, it will further decrease. If I go to 1200 RPM, it can further decrease. So a big diffusion layer can be made very thin by simply rotating the electrode. That means a semi-infinite problem can be turned into a finite problem by doing a rotating disk electrode experiment. So that is what we are going to do now. What we are going to do? So I have set up an experiment wherein I have a gold disc as an electrode, reference electrode is silver chloride, platinum mesh is a counter electrode. The electrolyte is potassium ferrocyanide and ferricyanide in a sodium sulfate supporting electrolyte. Okay, so this is our experiment. Now we are going to do that quickly. You will see. So this is a rotating disc electrode experiment. This black line is a CV, that means at 0 RPM. So this peak is oxidation of ferro to ferri, and this peak is reduction of ferri to ferro. And when I start rotating at 300 RPM, you will see the current is increasing. So this is called limiting current. Okay, that's a maximum current which is possible for a given rotation because the species only diffuses at that speed. Beyond that, it cannot diffuse. Okay, so and then when I increase the rotation speed 600, 900, 1200, you see that the limiting current goes up. Okay, but not much change in this region because this is a kinetic region wherein only the potential influences the current, not the mass transport. So mass transport influence you will see at the limiting region very much. Okay, so this is our experiment that we have done. Now what we do, we can do this experiment, impedance study, at 4 or 5 different potential along this LSV, linear speed potentiometry. Okay, so let's do that. Now first I am doing it to open circuit condition. When I do it at open circuit condition, I have certain impedance data. You can see there is one value here. This is due to solution resistance, and I have a semicircle here. The semicircle is due to the charge transfer resistance, okay, of the ferro-ferri species. Okay. After that, I see a 45-degree angle. I see a line, right? At 0 RPM, I see a line at 45-degree angle. Why this is due? This is due to, this is due to a Warburg. That means due to the inability of the species to diffuse towards the electrode. Okay, so basically you have a Warburg impedance, then you'll have this 45-degree angle line. Okay, this can be easily derived, this equation, using the fixed second law, but I am not doing that here. But what is interesting, you can see when I go to 300 RPM, what was a 45-degree angle line? Now it started bending and forms a semicircle. And semicircle even becoming better at 600, 900 and 1200 RPM. It becomes even smaller in diameter. But in all these rotations, what I don't see is a change in the first semicircle diameter. That doesn't change at all. Why? Because that's related to the kinetics. That is kinetics of the reaction happening at the electrode-electrode interface. That's not changing. What is changing when I rotate is only mass transport that is changing. Therefore, from 0 RPM to 300, 600, when I go, I do see a change in the mass transfer region. This frequency region, remember, this is a low frequency region. It is in the millihertz. That's where you will see the species diffusion as per the table I have shown you in the beginning. Okay. So you can see that mass transfer is becoming better and better. Therefore, the resistance, which is the diameter of the semicircle, is shrinking as you increase the rotation. Okay. So now let us look at this Bode plot also. So you can see there is no change in this region at high frequency. You will only see changes in the low frequency region. Okay. So now this is what, when you come back, you can understand. So I had initially a very big diffusion layer if I don't rotate the electrode, but by rotating the electrode, I compress it. So when I compress it, then it's easy for the species to diffuse into the electrode because I am having high concentrated species at this point. Why? How I got the high concentrated species over here? Because I'm rotating the electrode. Solution is drawn towards the electrode. Okay. Now let us look at this. How do you perform this experiment in generally? Generally, students, as soon as they assemble the battery, they go for impedance. So you need to make sure your system is at equilibrium first. As soon as you assemble the battery, probably it is not at equilibrium. Electrolyte would have not gone well into the electrode pores and so on. So you have to leave for some time. So what we have done is we have done the impedance at different interval of time. Whenever we got the stable impedance, you see at 80 minutes and 100 minutes, there is no change. Only then we can go for the impedance measurement. So if you are making a cell, I have seen often literature wherein people make lithium-ion battery. As soon as they make, they measure on impedance. After a few cycles, they will measure on impedance, and then they claim there is a decrease in impedance. True, there is a decrease in impedance, but there is no surprise, nothing surprising in that. Okay, therefore you should allow the system first equilibrate and then do this measurement. And then here you can see at different time, I have at 1 RPM at different time I have done again. So again, there is a stable impedance comes between 80 to 100 minutes. Okay, so therefore I made this experiment and waited for 80 minutes, then conducted this impedance. Okay, right? So, as I told you, Warburg is a circuit element that describes the impedance of an electroactive species which is diffusing to or away from the interface of our electrode. So this Warburg in your impedance circuits, they are given with the symbol W. Okay, so where the electrode is a place where the as a Faraday reaction happens, and you have a semi-infinite diffusion layer, and the species comes from the bulk to the surface. Okay, so that is what is described by your Warburg impedance. If it comes faster, that means if your diffusion layer is thinner, okay, it will come faster, because if you look at the diffusing time scale, compare it with this, the frequency, you will have a clear understanding that yes, now the species at this rate will make to the electrode in a given time where I am doing my experiment. Therefore, you will see them as a finite diffusion model in this system. Okay, so how thick finite? When will you see the finite Warburg? How thick a BL can be? I mean, so you can see here. You can use this equation delta square root pi by t, where this d is the diffusion coefficient of the species, and t is the time that you are waiting. From there, you can understand what will be the thickness of the diffusion layer. The delta is the diffusion layer thickness. If the diffusion layer thickness is too much, you will not see. With rotation, we can make the the diffusion layer thickness very small. Therefore, you can convert into a finite BL. Okay, so when you make it a finite BL, instead of W, there is a symbol O in your circuit element. So you can use that, and you can model this finite diffusion thing in your interface that is supplied by the vendor of potentiostat galvanostat. Okay, so with this, maybe only one last slide. So if you look at the semi-infinite Warburg impedance, you can also extrapolate it. So you had a 45-degree angle, there is some points, right? Imagine I am going to extrapolate it. So it will form a very big semicircle. Okay. So all I have done by rotating the electrode, I have reduced the thickness of the diffusion layer. Therefore, I have made the semicircle very finite. I can make the species diffuse to the electrode in a meaningful time. Okay. So you can also look at like this. As if an ink dropped into the solution, I mean water. If you try to sample after dropping the ink, if you sample the solution at the edges or at the boundaries of this beaker, okay, you may not detect the ink, or you may detect the ink at these locations after very long time. Very long time means which is beyond the time that I'm waiting for to make this measurement. Okay, so that may not you may not see, but actually ink is there, it is diffusing, we all know, but it is not making to that boundary point. Okay, so that is a semi-infinite diffusion. But if you stir the solution, imagine after dropping this, I put a stir bar and stir it, then you probe the solution at the edge, at the boundary, you will immediately detect the ink, right? So it's the same thing. So by rotating the electrode, I kind of stir the solution, made sure the species reach the electrode. Therefore, I can detect its signature in the impedance spectroscopy. So that's all about it. So you can look at that way. So I thank my students for making this excellent presentation to present to you. And with this, I conclude my lecture. And if you have any questions, please.
Thank you very much, Professor Ramanujam, for this informative and engaging lecture, which was including impedance fundamentals in batteries, capacitors, inductors, and also you have explained different types of rental circuits. So I'm sure the
Hello.
students and participants must have greatly benefited from your talk, and it must have sparked many questions and new ideas in their minds. So we are open for the Q&A session. Maybe I will read the questions from the chat box for you. So first question is, could you please explain the reason behind series and parallel combination in Rendell circuit?
I think sir has left due to some networking problem. Maybe we can wait for him to rejoin.
Okay.
Can you hear me? Hello.
Yes, sir, you are audible.
Okay, was my talk was completed? Because I came out and saw it was unresponsive my page.
Okay, yeah. Swapna, can you uh,
Your talk was completed. We
Okay,
will now take questions. It was a very wonderful talk,
thank
very informative. So, Swapna, you can take question.
Yes. So first question is, so can you suggest after how many cycles we should take the EIS measurements to get the distinction?
Oh, there's a trial and error they have to do. It depends on the electrode electrolyte interface. So as I suggested, they have to repeat after every few minutes and then check whether the response is same as the previous attempt. If it is, yes, that means it reached the right state to begin the measurement.
Okay. I hope it's clear to the participants. Next question is, please explain EIS of the metal ion hybrid capacitors and the EDLS.
ED?
LS, it's
EDLC, it's the
LC,
double layer.
EDLC.
EDLC. Okay.
Yes, yes.
So in EDLC capacitor, you have only capacitance, strict capacitance. Okay, there won't be any. If you look at the Randall's circuit, you will have only the solution resistance followed by a capacitance. Okay, it's a linear RC circuit. Whereas if you are taking a metal ion capacitor, things like that, there are some surface redox reactions that happens, which gives you that additional capacitance. Therefore, you will be having a charge transfer resistance associated with that. Therefore, accordingly, you have to change the impedance fitting. Okay, but in a perfect EDLC, you will not have a RCT or that resistance which was parallel to the capacitor. No, that won't be there.
Okay. So next question is, what will happen to the ion diffusion process if the phase angle approaches more negative?
It can become maximum 90. Okay, nothing will happen. So it tells you your interface is more capacitive in nature. That's all it tells you. So if your interface more capacitive in nature, whatever the current you are passing, a fraction of it goes for energy storage by capacitance mode. A fraction of it goes for the charge transfer reactions. Once your entire surface is now charged, then whatever the charge you are sending will now only go for the Faraday reaction. Okay. So it will not go for any, because already the interface is charged. So it only changes the profile, that IT profile, current versus time profile, as soon as you apply the potential, right? So only it changes that. So if you don't want your interface to be more capacitive in nature, it has to be more, for example, sensors, if you take metal ion sensors or trace metal ion sensors. If you take trace metal ion sensors, already the metal ion concentration is very low in the electrolyte. And if your electrode is having a very high double layer capacitance, then what will happen? You will have a very high current, but most of it is due to your double layer. So then you will not be able to distinguish one low concentration from another low concentration. You will have the same results. Therefore, it cannot be used as a sensor. Whereas if you have an electrode wherein the interfacial capacitance is very low, and the charge transfer resistance is dominating in that case, then you will see for each solution concentration a distinct output. So that is where it's important. Okay.
Okay. One next question is, could you please explain the reason behind series and parallel combination Rendell circuit?
Yeah, whatever the elements which are in series in the battery or any electrochemical device, we'll put it in series. For example, if you have a case of a battery, then a metal ion battery, for example, lithium has to come from the solution into the electrode. So therefore, movement of the lithium through the electrode, that means it depends on the electrolyte conduction. So that will be in series with what is happening at the electrode-electrolyte interface, because only if this lithium goes there, then whatever happens at the electrode-electrolyte interface will happen. Okay, therefore we have put these two in series. So the impedance due to the electrolyte will be in series with the impedance due to electrode. But in the impedance due to electrode, there can be multiple processes of the electrode. As I told, the charge may be stored in a capacitor mode, or it may be stored by intercalation deintercalation process. Therefore, that impedance will have to be split into two. One is due to this redox reaction or intercalation deintercalation. Another one is due to the charge storage at the double layer. Therefore, that impedance is split into two and they are put in parallel, because the current that comes from the electrolyte can go to any of these two processes, and these two processes are in parallel. Therefore, I put a resistor and then a capacitor and then again a resistor in parallel to the capacitor.
Okay. Thank you, sir. I think I'll take just one or two more questions. How can we determine the time constant with this impedance?
So you already have this R value from the diameter of the semicircle. And I have told you the top of the semicircle is a characteristic frequency, which is equivalent to, which is omega RC equivalent to 1. Okay, omega RC equal to 1. So now you know the omega because you can read from the instrument what is the frequency correspond to that point. So you know the omega, you know the R from the diameter, therefore the C can be calculated from that equation.
Okay. Next question is, sir, which equivalent circuit should we choose for our circuit problem?
That's why.
Like,
First, you should know what is the battery that you have assembled. Suppose, let me take an example. I have a organic metal ion battery. So I'm using, say, lithium one side. The other side, I'm using an organic cathode material. What can happen at the organic cathode material? Your organic cathode material may be reduced, and probably a proton from the solution might be involved in that, or the lithium, or if it's a zinc metal ion battery, the zinc may be involved in that. Okay, so you have two processes now. One is if you have a zinc in one side and you have organic cathode material in one side, so when you are doing a discharge, zinc dissolves in the from the anode and comes to the cathode. Now your organic material may undergo reduction and the zinc may coordinate to that ligand. Okay, or organic metal may undergo reduction, but proton may be coordinating with that ligand. Okay, but proton is much smaller compared to zinc and it can easily intercalate into that material or easily insert into that material. Therefore, the time constant for the reduction in presence of proton will be different from the time constant for the reduction in presence of zinc. Okay, although organic material is undergoing reduction, but the ion which is involved during the reduction is different. It can be proton, it can be zinc, it depends on the potential you apply. Okay, so therefore now I have the same reduction process but with the two different time constant. Then what you have to do, you have to have a two RC circuit which should be put in parallel to each other. Okay, and then a solution resistance. Okay, how I am able to determine that? Because I have already done the cyclic voltammetry of that electrode and I found two peak for the reduction. One peak from the literature I understood it is due to the zinc insertion. Other peak is probably due to the proton insertion. Therefore, from that CV, I have some information upfront that there are two types of reduction that is happening, and hence I can use that information while selecting the proper equivalent circuit for my model. Okay, so this all, as I told you, you have to combine other analytical techniques and have some idea. With that, you have to choose it.
okay. Thank you, sir. Maybe this is the last question. And why sometimes there is no proper semicircle at the high frequency region? Is it based on some voltage that we are applying? What type of voltage we can apply to have a proper characteristic of the material?
This is what I want to tell the students. When you are doing an experiment, first of all, why are you expecting all the time semicircle? You should not. Okay, you can have some expectation based on the information you have from the other analytical techniques or other results that you have about that material. You can have some expectation, but every time expecting a semicircle is not right. Okay, and again at high frequency it need not come, because only if there's a charge transfer reaction that happens, then it would respond that way. If there is no charge transfer reaction, then it not necessary it has to respond. For example, if you are doing at open circuit condition, the resistance involved in a charge transfer reaction is very high. As I told you, you have to imagine as if in a chemical kinetics, you have a rate of the reaction which is proportional to the e power minus EA by RT, right? EA is activation energy. So at very close to equilibrium, at open circuit condition, you would see that EA is be very high. So with the magnitude of the perturbation you give, 5 millivolt or 10 millivolt, probably you are not at the region where the EI is really small, that you would see a finite resistance. You may have a very big resistance, so therefore the points will start scattering, okay, or it will form a semicircle. Only when you go to very, very low frequency, then it will form a full semicircle, okay. So you cannot expect that. So first you decided what DC potential you wanted to do this AC measurement, okay. So and then you choose that potential, and on that potential you apply this AC perturbation, then you might see a semicircle, okay. Sometimes what happens, the inductive processes will respond, especially at very high frequency. So suppose your wires are exposed, and then the current flowing, the AC current that is flowing in the one wire is influencing the other wire, then you would see there is an induction of electricity on the other wire. Therefore, you will see some complicated impedance showing up in your system. So if your cables are well insulated and they are well connected to your electrode, and you are in a region where the activation energy is finite, then you may get a nice semicircle. Otherwise, it may not. Okay.
Thank you so much, sir. So I think we can close the Q&A session. So I would like to thank you again, sir, Professor Ramanujam, for engaging so thoughtfully with the participants and for a truly valuable session. And thank you all the participants for joining us today. We look forward to seeing you in the upcoming sessions in the webinar series and also participation in NSEST 2025 conference, which is to be scheduled at SRM at Chennai. And one more thing that I want to add on for the participants, that is the participation certificates will be provided to those participants who will attend all the lectures from this series. So Dr. Pooja, you want to add something?
No, I think I just would like to thank Professor Ramanuj for a very clear lecture covering lots of, I think, fundamental doubts. From the question, I can see that these are very common questions asked by the student who are entering into electrochemistry. And I believe with your lecture, it will sharpen their concept and strengthen their fundamentals. So I thank you again as a valuable ECSI member. So thank you so much. And I request all the participants to register for the conference also. We already shared the link for the conference, which is scheduled in August.